fly. And I'm going to show you this in an example. It's when the gradient doesn't change sign. So if things are unstable and it's not going to an equilibrium value, then the gradient will change its sign, right? If it's rotating around, and the gradient, if you remember, is the derivative with respect to x and the derivative with respect to y. If it's going around a circle, so let me just do a graphic here. If this is happening, the gradient would be the normal to this thing, right? So if you remember, like you're going around the circle, if you're going actually around the circle, the gradient's going to be, the derivative is going to be in the x direction, going to change its sign. Like if you think about the tangents as you're going around, the slopes of these tangents as you're going around are going to change signs every time it increases or decreases around the circle. So if you know that it's not changing its sign, then it's either coming all in or it's going all out. So then you can say I can eliminate this possibility of happening. So that's it. Dulac criterion, gradient f doesn't change sign implies f y prime equals f has no periodic solutions. If you have something that you're modeling and Nico, are you taking notes? I need your full attention. I need to know that you're ready, like from what I show you here, to come and take the T. I've done my job. All right, so here, all you do is you just take the gradient of the right-hand side and show it doesn't change sign. So there's a whole bunch of questions in the book that are of this nature. I would study up pulling one of those to see how it works. So I pulled the first one, so you shouldn't do that one. Here's an example running through it. And it only works for planar equations, which means 2 dimensions. West Nile was 2 dimensions. Now I'm like, it's driving me nuts. So your right-hand side, I shouldn't have drawn a little f, it's a capital F. Your right-hand side looks like, as in vector form, it's going to look like this. This is the first component. That's the second component. Vector form, the way you did in Jedi Math, 255, 205. So here's step 1. Write as a vector. Step 2 is just to find the gradient. To find the fx and fy, and so do this scratch. Fx turns out to be 3x squared. Fy turns out to be 2 plus x squared. Sorry. Yes, that's right. So second equation. to find the gradient. Of the second equation, you look to find the derivative of y. So you get 2 plus x squared plus, they put a 1/3 in front of the y, so you just get y squared. You take the derivative by power rule, kind of done. And then make your solution. That's what happened. Why isn't it good enough to just simulate this thing on Dr. Grove's? Why is that not enough? Why can't I just simulate that and say, I don't see any periodic solutions?
I think it goes back to the example we had recently run through inside something, you're going to converge to the point with your house, so you're going to come to that like outer boundary, like those little changes and do things we don't expect. It's like just because showing that one example isn't periodic.
That's right. There's an infinite number of initial conditions you could possibly check. And if you ran it and you saw no periodic solutions in your window, it doesn't mean that there's some point out there that does something really weird that you didn't ever see before. So that's why numerical, it's the same reason we make our math majors take pure math classes. How many of you are anybody OR in here? Everybody's math side or data science? Okay, everybody's math side. So you will be taking real analysis foundations. If you're taking foundations, I recommend taking it in the fall with Dr. Groves is teaching it. Because she's gonna, I can't guarantee like if you go too far out, she's gonna adopt the plan that I have where you would get revisions to your proofs and get 2 chances to do the proofs with some feedback. It's really hard to learn how to write proofs without that support. And if somebody teaches it 2 years down the line, that's not a guarantee that's gonna happen. So recommend that you take it. You already know her from her, but that's what makes the difference. Like, yes, she is. Go ahead.
Can you show me how you got x and f?
I went to the first right-hand side, and I just went, what's the derivative with respect to x? Oh, I lost a 1.
Okay.
1, 2x.
2x.
This is a cube, I think. Because in my notes I have a cube. Yeah, that's right. In my notes I had a cube. It turned out to be a square when I put it on the board. And then, so I go into the first equation, 1, 3x squared, and I go to the second equation, and I get 2x squared, 3 times 1/3 xy squared, so I get this guy.
And it's not like a Jacobian where you're trying to do x and y, x and y. It's just the x of the x.
Yes.
Driven.
Yeah. Because the first equation is telling you about the slope in the x direction. The second equation is telling you about the slope in the y direction. And if the gradient of that doesn't change sign, then the slopes will be going in the same direction. The original equations will be going in the same direction.
So I guess you're finding the gradient. So you're finding the rate of change of
the rate of change, right? So you're saying something about the derivative, actually. The derivative can't do certain things, right? It can't do this winding around.
So it doesn't change sign. You can't wind around.
Yes, it can't wind around. But it's a pretty nifty tool, and I've used it. So I've used it for theoretical stuff, just to show something about my equations. And the reason I can't numerically simulate and get away with that is because there could be some possibility where it's not true.
I forget the actual term for this, but is that opposite true? Like if it does change, like if there is a change in sign, does that mean that there is a periodic solution?
No, you could have weird things happening. Like um, you could get like these hyperbolas going out. You've seen those face portraits where you have a bunch of hyperbolas going out in two directions. You could get all kinds of weird. You could have saddle. So you could have all kinds of possibilities the other direction.
This is
Just to eliminate. There's no way that you could have a periodic solution.
And so you would use compare or see if there's the solution.
Yes, you'd have to use Poincaré to prove it. Yeah.
Both were all negative, then you would sort of be the solution for the all negative.
If the gradient's all negative. So there is a section that we skipped out of the book about Lyapunov stability, which is actually the way you show with gradients what's happening, that you can trap your solution in certain things, then you can say more about your solution. So engineers use that. So you're going in that direction. There's a little bit more to it than just like find the gradient. You have to kind of show something about my solutions being trapped inside these circles, not circles, but like shapes. So I can say something. They're called energy equations. So that's where you're going to. I looked at that section, I was delighted to see it, like, oh, it's not in the pacing schedule. So, but if you go into engineering, you'll do more of that.